Hello and welcome to a video on phase shift oscillators. In this video we will have a look at the principle on which a phase shift oscillator works, the derivation of equations using Barkhausen, some variations on the RC phase shift oscillator, then we will do some problems and some simulations. Okay, so a phase shift oscillator is basically inverting amplifier with some RC stages, right? And every RC stage can have a phase shift of up to 90 degrees, right? But for that you require an infinite amount of frequency, right? So we'll start off at 0 and at infinite it will be 90 degrees shift. Okay, so we need at least 3 sections to make this possible. Theoretically, you only need 2 to make a phase shift of 180 degrees as required by Barkhausen's criteria. Okay, but since we're not going to put this at infinite frequency, we need at least 3 sections, and each section will contribute about 60 degrees of phase shift. Okay, so to visualize this, I plotted the phase shift of 1 to 4 RC sections that's connected in series like we have here. So for 1 we have a 90-degree shift. Okay, so that is from 0 to 100 megahertz. Okay, and this is not even at the 90 yet. Okay, 2 sections we have 180 degrees phase shift, and 3 sections 270. And if we look here in the middle, where we have a 0 to 180 shift, that's about 60 degrees that every section is adding. Okay, so the oscillation frequency for 3 sections will be in this area right here. Right, so the basic principle is 3 sections like this with inverting amplifier, and it's being fed back into the amplifier. So this provides a phase shift of 180 degrees, and this provides a phase shift of 180 degrees, bringing us to a 0-degree shift as required by Barkhausen. Okay, the typical configuration will leave out this one resistor right here. So I will show you in the next slide why it's not necessary to include this resistor. Okay, so with Barkhausen we need to get a loop gain of 1 and a phase shift of 0 and ensure that our circuit starts up automatically. So for this first resistor, why it's typically left out in designs is if we assume a ideal op amp, there is no current really flowing here, right? So the assumption is that there is no current flowing into the op amp. So no current flowing in this resistor. So technically we can just leave this resistor out and work on the input impedance of this amplifier here, which is also infinite. Okay, so we leave this one resistor and we still have 3 RC sections basically. So no current flowing through this resistor, and we can leave it out in our derivation. Alright, so the first assumption is ideal amplifier. So the 2 input voltages here being forced to 0 with a virtual ground, and there is no currents flowing into the amplifier. Okay, we break the feedback loop and we call this part VF and this part V out, and we view our system from the input here. So we define our currents to do a Kirchhoff's current law. So select all the currents flowing into this first node, select all the currents flowing out of the second node, and again select all the currents flowing into the third node. So the sum of the currents here is 0, the sum of the currents here is 0, and the sum of the currents here is 0. And we can set up 3 different equations. So Vf minus V1 over the impedance here, so Zc. So Zc is 1 over Cs. So what you see here is just a conversion from Zc to 1 over Cs, which becomes a multiplication. So this voltage minus that voltage divided by the impedance. Since this current is flowing upwards and we define our voltage as plus minus like this, minus V1 over R, and backwards from here V2 minus V1 over Zc. And there we have our first equation. Same for the second, V2 minus V1 over Zc, V2 over R, and this is a plus because we defined it in the correct direction, plus V2 over R, and then V2 minus Vn over Zc again. Okay, and we know that this Vn is a 0. So in the simplified format here, it is gone. The last equation, V2 minus Vn over Zc, current added from the amplifier, and V out minus Vn over Rf. And we also know that this is 0, that is 0, and that is 0 with the assumption of a ideal amplifier. And we have 3 equations, and we have in these equations 2 unknowns that we want to get rid of. Okay, so what we want to get to is V out over Vf with a phase shift of 0 and a loop gain of 1. So here is our 3 equations from the previous page. So what you want to do is you want to take V2 and substitute it into these equations, and the resulting V1 want to substitute it in there. And then in this top equation, what you will have left is the V out and the Vf and all the resistors and capacitors. So you can pause this and do this on your own, the substitution. So I first did the V2 into V1 here, and then both up into the top equation, and then I started to simplify down to this point. So if we want V out over Vf, we must divide by Vf and then take all of this and over to that side. So multiply with RFCS and divide by this bracket over here. Bringing us to a very simple equation of minus RFR C squared S squared over 1 over RCS plus 4 plus 3 times RCS. Replace all the S's with J omega, and here we will have J omega squared, and this will be minus 1 omega squared, so the negative signs will cancel. And down here we will have a 4 which has no influence on the phase, and 2 imaginary terms. Okay, so this term over here which has imaginary values in it, we should set that equal to 0, and that will be our phase requirement, and the remainder will be our loop requirement for our gain. So this will provide our frequency of oscillation, and the remainder will provide our required gain to start the oscillation. So, equating this to 0, we will find that our oscillation frequency is 1 over 2 pi root of 3 times RC. Okay, and then we are left with RF RC squared omega 0 squared. Okay, so we resubstitute this omega squared in here. Okay, and then we will get that the ratio between RF and R is just 12. Okay, so for oscillation to start, RF over R need to be larger than 12. Right. Okay, so there is our design equations. So the variation is the circuit on the right hand side, where you will typically find that there is an extra resistor included going into the amplifier like this. So what you have is basically a high pass filter and two RC sections. If you redo the whole Barkhuizen's criteria thing, you will find that it is the root of 6 and the gain should be larger than 29. So be careful when you browse around not to think that this is also just the root of 3 and the gain should be 12. And most of the time, the gain for these two variations is confused by people. You will find this circuit and a root of 3 here, and you will find this circuit and the ratio of 29. So just be careful not to make that mistake. Oh, obviously this one will work with a gain of 29. But yeah, your frequency for this circuit will be off if you implement it. Okay, so the practical kind, you will typically use the one with only the 2 resistors, so that the resistor that you add in here does not affect it when you have non-linear amplitude control. Okay, and the gain of this amplifier is RF over R, as we already found out while doing our derivation. Okay, so the automatic gain control is the inverting kind, so no funny things that you should do with the equations like with the Weinberg oscillator to get things to work out. And if you have no idea about the non-linear gain control, go and watch the video on that. So the problem that I want you to do is to design a RC phase shift oscillator with amplitude control here. So at 10 kilohertz using 3.3 nanofarad capacitors. So when this thing should start up, our gain should be more than 12. So the limiter designed for a gain larger than 12. And when we limit the output to plus minus 5 volts, assuming a rail voltage of plus minus 10 voltage, the limiting gain should be 0.4 volts per volts. Use silicon diodes, calculate all the required components, select E12 values, and simulate the problem. Pause the video and go and do that, and I will be back with a solution in a moment. Alright, so the design is kind of straightforward. We take our oscillation frequency, 10 kilohertz, plug it in here, take the 3.3 nanofarad capacitors, place them in here, and we will find that we have 2.7 kilo ohm resistors that we should be using, and that will take our oscillation frequency to 10.3 kilohertz if we put all the selected values up in here. Okay, so our frequency will be a bit off. If you want it precise, use E24 resistor values, or just try to figure out a better ratio for the resistors. Okay, But remember that your component choices will have a influence on the frequency. Okay, RF over R should be larger than 12. So R was 2.7 kiloohms. This gives us 32.4 kilo. 33 would be the obvious choice for RF to ensure that we have a gain of 12. But I would rather go to the 39, which will ensure that our oscillator will start up. 32.4 to 33 kiloohms is a bit on the edge. Okay, so for the gain control, our gain is now 14.44 for the resistor values that we have chosen. We want to limit to plus minus 5 volts, and we want to take it down to 0.4 volts, volts per volts. Sorry. Okay. So calculating R4 and R3, we get 1.1 kiloohms. The closest is 1.2 kiloohms. Calculating R5 will give us 3 kiloohms, and the two choices is 2.7 and 3.3 kiloohms, and I would rather go with 2.7, which will give us a larger amplitude and compensate for any losses that we might have due to our choices. In simulation, if it doesn't work out, just go with 3.3. Okay, that is always why you simulate a problem before building something. So let's go over to the simulations and see if all of this works. The first simulation here, I built our basic oscillator that we just designed, and I took the variation with a resistor and I adapted it to have oscillation of 10 kilohertz, but that required some different component choices. And you'll see that if you take 5.6 and multiply it by 29, you would get something more in the range of 180k. If you go with 12, this should be about 68 kiloohms. Okay, so this one gain of 12, this one gain of 29. Let's run them. Okay, see the oscillation start, but it clips, and the oscillation starts, but it clips. Okay, let's change this to our 68 kiloohms and try it again. We'll see that this oscillator does not start up. Go to 82 kiloohms. Oscillator still doesn't start up. 150k. Nothing. 180 kilo. And it starts. Okay. So this you can see that the ratio is 12 and this one needs 29 at least to work. Okay, so just be mindful of that. Okay, let's jump over to the simulation with. So here is our two simulations. One without gain control, one with gain control. Let's run it. You'll see that I allocated a lot of time here. Okay, because I want to do the FFT. So let's just select both signals. And you will see that the one is clipping and the one is between plus minus 5 volts and looks a lot better. Okay, so here is the problem that you had to do, and it simulates perfectly. Okay, let's take this and let's do a FFT on these two signals. Let's run it, and you will see that there is a much larger harmonics in the green signal and smaller harmonics in the blue signal over here. Okay, so and when zooming in, you can see that one is more pure than the other. And with the FFT, you can also see that the blue here is more on the 10 kilohertz than the green one. Okay, by adding the gain control, there is a bit of a shift in frequency. So yeah, always some of the components will have effects that you don't think about because it is assumptions that you make while designing for these. Okay, and that is it on phase shift oscillators. Thank you for watching.